Okay, so we will start RNNs today. Okay, so what we have seen so far is that once again, yeah. So what we have seen so far is are different ways to learn word embeddings, CBOW, skipgram, SVD, and all that, right? So all that is used that solves the problem somewhat of representing words in the form of vectors, right? Dense vectors, which we can then subsequently use in other ML problems, right? So what we have solved so far, or at least some so far, what we have is arrived at is to arrive at a representation for words, okay? And these are dense representations that try to capture the relationship between words and the surrounding context in some sense, right? So that's what we have tried to do. We have been reasonably successful, though not entirely successful. Okay. So now what we have to do is this is just the input. So the reason text data is difficult to work with is the input itself has to be figured out, right? How to represent the input in a proper form. So that itself took so much time. Now, once the input is in a form that is consumable by a neural network, we can now go and look at what kind of neural network will solve our problem. Okay, so the first approach, we will take a typical NLP problem, right? And we'll use that as the prototypical problem to introduce recurrent neural networks. So that will be sentiment classification, right? So just to keep things simple, sentiment classification is what we are interested in. So you have a corpus, training corpus with pairs of the form x comma y, where not x comma y. So it's more of, just to be clear, this is x1. This itself is a pair, right? So let me write that down in separate line. So the the input is of this form. So you have x1 dot 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 x, say capital T. So that's T time steps or T words in your sentence, sorry, in your paragraph. And your expected output is y, right? And this y belongs to, let's say, 0, 1, 2. So 0 means, or let me just, so positive sentiment, negative sentiment, and maybe neutral, right? So that's something called neutral, where you're not, the movie was not too good or too bad, right? So sentiment classification may be particularly movie reviews, right? So we could put it that way. All right. So this is a problem setting that we are going to consider. So based on our knowledge of working with feed forward networks, what we can do is one approach to solving this problem, right? So the first approach is to consider a feed forward network with a, so remember that what do you want to do? You want to predict the sentiment, but then you can't do it one word at a time, right? So the problem of, so you can pass one word at a time to your feed forward network, but if you pass one word as input, it will produce some output, right? So it will be positive, negative, neutral at every time step, and that cannot give you any information, right? So your feed forward network cannot arrive at a decision by just looking at one word. So what it needs is a context of words, right? So you can consider a feed forward network that works with some sequence of words. Okay. So for instance, it could work with sequences of length 3. Okay. So it could work with, for example, what do I mean by that? If your corpus, if your paragraph that is summarizing a movie, right? It is of the form, the movie lead actor had done a terrible job. The movie is not worth a watch. Okay. So what do I mean by sequence length of 3? It could mean, say, you pass 3 words at a time to your network. So the lead actor, and then you pass had done a terrible job. The right. So things like this. So what you now have is a slightly longer context, but then what you can do is maybe you can collect the individual labels at each, for each window that you pass to the feed forward network. Okay, and then maybe you could work with that. You could try to work with that. So you can maybe add all these three, you could concatenate these three labels, or you could maybe add them together. You could do some sort of jugaad and try to, fit a feed forward network to try and solve this problem. But you can quickly see that such an approach may not work that well, because a context length of 3 is too small. So just to give you an idea, so if you have a context length of 3, you'll end up with something like worth a watch. Whereas in this case, a context length of 4 might have been better. Not worth a watch, negative sentiment; worth a watch, positive sentiment. So even if you could manage to train a feed forward network, what is a limitation? Finite sentence length or finite window size, right? So this is a window size, right? It's a limitation. Okay. So your context, even if the context is very big, even if you can feed 10 words at a time to your feed forward network, you will still run the risk of having, movie reviews that work with longer contexts. Okay. So a feed forward network is really not a good idea to try and solve this problem. So is this idea clear? Why feed an existing network, the existing feed forward networks cannot really be adapted to solve sequence learning problems? Is clear with everyone, right? Any questions regarding this point? Okay, right. So the conclusion is that feed forward networks are not suitable for solving problems where the input takes the form of a sequence. Okay, reason, you'll have to somehow break down your input into finite windows and feed those finite sequences to your network, and that may not work well because your sequence length is not something that is fixed. It will keep varying, and if you start breaking up your sentences like that or your sequences like that, they may not really help you learn the underlying structure. Okay, so what researchers finally came with was a very natural extension to this idea, which is called a recurrent neural network. So what we try to do here is, we know that there is a temporal dependency, right? So there is a time dependency. So we will, what they try to do is, you have xt, okay? So you know that there is, at time step t, your input to your network is going to be xt. Now, what do we do traditionally? So if this is the only thing that's there, then maybe you have some sigmoid function that operates on this input. So let me, give me 1 second. We need to pull up this. This is a neuron, right? This is a sigmoid neuron. Okay. So what happens to the sigmoid neuron? Your usual some linear combination you have to do, right? Before you pass it to the activation function. So let's say you multiply it by some weight matrix u. Okay, and then that's the hidden layer. So you now have an output layer. So what could that output layer have? So the output layer, let's say, gives you, so y hat, right? Some predicted label, and there is again some weight matrix that transfers the hidden layer to the output layer, right? So let's call that v. Okay. Now, ideally, this is just one time step, but then because there is a time dependency, what you would like to have is some notion of the dependence of the current time step on all the time steps that have come before you. Okay, so what researchers actually tried to do was to introduce this concept called a state vector. Okay, so what this will do is, this st minus 1 in this case will capture whatever information is necessary, okay, to help in making this decision at the current time step. Okay, so what they did is they added this new concept called the state. So this is a, that comes from the previous time step. Now this is not going to just pass without any modification. So this is also going to be modified by some weight matrix w. All right. So now what you have is, you have st minus 1 coming from the previous time step modified by w, and then you have xt coming from the current time step. Together they will combine to produce st, and st, what you can now do is you can pass on this information called st. So this is st, okay, in two directions. One is forward. So whatever information you have collected at the current time step, that is st, you forward it to the next time step, and at the same time you also use that st to make some decision at the current time step, some prediction at the current time step. Okay, this w, what happens is, this w is kind of carried forward, not just w but u and v. So you don't have new weight matrices for every time step. Instead you have one set of weight matrices u, v, w at every single time step. Okay, so is this basic idea clear to all of you, what is happening in a recurrent neural network? Okay, right. So
Sir,
the way, yeah,
sir, can you explain once again? I did not get it.
yeah. So when I take an example, it will become clear. So let me, in fact, it's better to, represent this in the traditional way, where so there is a this is a recurrent connection that's going through. So let me add that first. Should go back here, should go here. Okay, so this is what is meant by a recurrent connection, meaning there is a weight vector associated with the recurrent connection, and there is some weight vector associated with the input and something associated with the output. Okay.
So
Yeah,
is it mean like once the W, V, and U are learned, they will not change? I'm not getting like, will they be changing in the next time
I'll come
step
to this.
or?
So I'll come to that. Yeah. So there is this concept called unrolling an RNN in time. Okay, so that will give you a sense of what is really happening in a recurrent neural network. So same task. So as I mentioned before, we are only going to look at this task. So let us look at sentiment analysis for movie reviews, right? So let's look at this movie review. Very simple review. The movie, you don't need the so movie was excellent. Okay, this is the review, and this is the review, and this is the sentiment. Okay, and your RNN's goal task is to predict if the sentiment is positive or negative, right? Or neutral. This is the true label, by the way. Okay. So what do you now have? You have 3 time steps. Okay. So let me copy this and get rid of this. Okay. So let me get rid of this also and start from the left. What is x1, right? You start with the first input to your RNN, and that's movie. Okay, that's the word embedding for movie, by the way. So there is one step before you pass it to the recurrent neural network, which is what is movie? How is movie represented? This is what we have done all along, right? There will be some word embedding corresponding to movie that you have already learned. So you could do it 2 ways. You could have already learned some word embedding for movie, or you could use the RNN itself to learn the word embedding also. Okay, both of these things are possible, but we will for the present we'll assume that we are using what are called pre-trained word embeddings. Meaning you have used, let's say, CBOW. You have used, let's say, CBOW to learn word embeddings for all the words in the vocabulary. Okay, this is one possibility. So you have already used continuous bag of words and you have learned word embedding. So now there is a word embedding corresponding to each word in your vocabulary, which is what you are passing as input to your RNN. Okay, so this is one assumption. This is not binding. You could do it differently also. We'll study that later. So what do? There's this concept of state that I already mentioned. So to begin with, we don't have any state, so to speak. So there is a null state. So let's encode that. So the null state, let's call it S0, right? S0, let's say, is some vector of size 0.
So
Yeah.
here statements that particular time it is mentioning.
Sorry.
Here state meant to be the particular time or is it different?
State is, yeah. So hidden. So this is hidden state. Okay. But then every hidden state, see, every input and hidden state is going to be associated with some time step, right? Because the whole thing is recurrent in nature, no? So
Like a time series data, it's been.
yeah, so you need to encode it properly. So this is like what I mean by movie here is x1. So x1 is the movie. Okay, or movie is x1. What I call x1 is I want to call it explicitly movie, but then actually it's x1, right? So whatever
Okay.
you would call x1.
Like the first word input, right?
Yeah, the first input.
Okay.
Right? Everything is going to be indexed by time here. So in the lectures it is I, or you could use T also. It's all the same. It's just a change in.
Okay. So
Okay.
we are giving the input as well as the particular timestamp and what is the defense for that sentiment. We are
So
getting it out, right?
yeah. So currently you just have the input, and then you have some idea of some notion of context. So the state, you could think of the state as, so the state serves two purposes. I'll come to both of them. So the state, okay, ST is actually doing two things. One is it acts as a context vector that encodes all the information available to the network until time step t, meaning S3 will have whatever information you have gathered from time steps 1, 2, and 3, x1, x2, x3. Okay, to begin with is just S0. S0 has no context, right? Because you are at time step 0, nothing has, no action has happened so far. So S0 is kind of 0, 0, 0, whatever, right? It's a vector of zeros. That is one role. I'll come to the other role in a moment. So you have S0, which is passed as the context vector. You have x1, which is passed as input. Okay. And what happens? You do some computation using the input and the state, and you compute some output. So that is S1. Okay. So you compute S1 here. Currently, S1 is not passed to compute any output in the upward direction. Okay. So all that you are doing is you are computing S1, and then that's your state after one time step. So S1 now encodes whatever information you have after seeing the word movie. Okay. So you know what you do is you repeat this process. You pass S1 from here. I'll come to the weights also in a moment. For now, let's just have these things in place. So movie was, what was the word? Phrase? Movie was. So you are now ready to pass the next input to your computational unit, which is the neuron. And what is that going to do? That is going to take S1 as input and X2 also as input. Okay, it's going to take these two as inputs, and it's going to compute S2, right? And there's one more time step. So it is, the movie was excellent. So that goes here, and this goes here. And you pass S2 to this neuron and X3 to excellent. Now notice that this will compute. What will this compute? What will be the output that this computes? S3, correct?
Yes, 3 with information from S1 and S2.
Yeah. So S3 it will compute based on the knowledge from the context vector and the word, current word excellent, the word embedding for excellent. So you have S3, right? So S3 now has information about the entire sentence. Okay. Now you are in a position to make a decision whether the sentiment is positive or negative or neutral. So what you do is you pass this S3 through a, so this will become big. So let me not add anything here. It's not, let me just call this y hat, right? So I pass S3 through a decision unit that will now output my label. Okay, label. So probability distribution over the labels. Okay, let's say y hat turns out to be, in this case, remember it's a vector of probabilities, right? So it could be 0.7, 0.2, 0.1. Okay, this is the vector that it outputs. And based on this vector, you conclude that the output is positive. Okay, the sentiment is positive. All right, so this is your skeleton of your RNN. But what we have missed is, or what we have not explicitly mentioned is, how are the inputs transformed to these states, and how is the final state transformed into the vector of probabilities, right? So you what comes in here are the weight matrices. So for passing your embedding into your converting the embedding into a state, you use U matrix U and the matrix W for the recurrent connection, right? So W is the thing that is going to learn what aspect of the context I should work on. Okay, remember that W connects the previous state to the current state. Okay, so it's called the recurrent connection. So or the so this is called the matrix for the recurrent connection. Um,
So,
yeah,
sir, I have one question. So the S1
It's
will
9
be
o'clock.
sorry. Yeah.
determined. S1 will be determined by weight of S0 plus U of Xi plus by Si.
We'll come to the equation. Yeah, equation I have not yet discussed. So
No, I'm just asking. Like sigmoid of those functions would be the input, right?
we'll come to that. Yeah. So for now I'm just mentioning what will be the matrices, right? So the matrix W connects the two states, okay, two consecutive states. So what will W learn? It will learn things like what should I save, what information is important, and what part of the context is necessary for the next time step. Okay, what should be preserved, what should be destroyed, things like this. What will U? So this U matrix connects. What does it connect? Matrix that connects input to the state vector, right? So what is this doing? This is kind of telling you uh, this is telling you what part of the input or how should I modify the input so that that will help me pass on the information contained in this to the next state. Okay, so this is going to work with the input and extract whatever is essential to be passed on to the next state. And after all this, you have at the last time step, right? You have a matrix V along with a softmax function. So the matrix V, what will it do? Based on this S3. So S3 in some sense is the final state. And this can be treated like some kind of a summary vector. Okay. So this the final state. Okay. These are all random names that I am giving, but you can also this is called there's no technical term called summary vector, but I'm just giving you an idea. So the summary vector contains in one vector it contains the entire context, right? Or the entire sentence is summarized in this single vector, and now you are making a decision based on the single vector. So how is the decision made? You first transform it to using the matrix V, and then you have a softmax function. So you could treat this as some kind of a decision matrix. So V is some kind of a decision matrix. So is this clear so far? What we have, this is that diagram.
Excuse me, sir.
Yeah.
Here the sequence is the sentence that movie was excellent.
Yeah.
Is it? So these inputs are given one by one. Is it? That is the mean by the timing. That
Yeah.
is the first time step only movie will be given.
Yeah. It
Is
will
it
be
like
given
that?
step at a time.
No, I just want to verify whether I have understood it clearly. Then only
Yeah.
on the third step, the third word will be given as input. Is
Yeah.
it? And these W's are same for all these steps, is it?
Yeah. So the W, U, and V, the weight matrices are shared across all time steps. So this is what we mentioned when we were doing regularization, right? Parameter sharing.
Yes.
So this is parameter sharing.
Okay.
So W, W, U, V, the three weight matrices are shared across all time steps, right? So it's kind of essential you do this, right? So you don't want new weights. So one thing is, it'll be very costly, right? If you have say 100 words in a sentence, then you are going to have what, 100 into 3, right? 300 matrices, right? That is computationally simply too much of an overhead. So you're not going to do that. Instead, what you're going to do is you are going to have three matrices that are shared across all time steps, in the hope that these three matrices are sufficient to capture whatever information is necessary to find out the sentiment of a sentence.
Okay. And sir, after the softmax, actually, they should tally as 1, isn't it? This probability that you have
Right.
mentioned 9
Yeah.
only.
Yeah. Okay.
Okay. Okay.
Okay. So now, yeah. So the state has two roles. One is it acts as a context, and it also acts as a summary vector in some sense, right? In this case, it also acts. This is another role, right? That helps the network to make its final decision, right? So remember, both of these are roles played by the state vector. So one is it carries over information from one time step to the other, and at the end, it also helps in making a final decision whether this is a positive, negative, or neutral sentiment. Okay, so this will come in handy later, knowing that the state does both these things. Okay, so now we are ready to list down the equations of an RNN. So what are the equations? You have, I'll copy this and get rid of all the extraneous text, okay? So that we have only what is essential here. Okay, this also is not needed. I'll just get rid of these so that we only have x1, x2, x3. So the u will act here also, and the w will act here also.
So
yeah,
U and W are not constant, right?
so u and w are shared, but yeah, they are the weights, right? So weights are not constant, so the weights keep changing.
Okay, so it's W1, U1 like that.
Yeah, so they're not constant in the sense during training they will keep evolving, but once you train the model, they are fixed.
So in equations, will it be fixed or not?
Depends on what stage you are in, right? So it's just like a feed-forward network. In your feed-forward network, was W fixed or was it changing?
It was changing every now.
But only during training, right?
Yeah.
Same
Understood.
here.
Understood. Here also it will be changing.
Yeah, during training it will change. During inference, it will remain fixed. Okay, so
Okay.
the first thing is you have input. Okay, that is multiplied by some weight matrix. So it's a ux1, and then you have a recurrent connection. So there is a W which modifies the state at time steps 0, and there is some bias that you add. So let's for now ignore the bias. Okay, so this is the linear combination. Once you have a linear combination, as usual, you do a activation function on top of that. Okay, so this is your first state vector, state at time step 1. At the end of, so this will be S1. So what will S2 be? First you do a linear combination, so you do UX2, and then you do a WS1. So there's W, from previous time step you get S1, and then you do a sigmoid. Okay, so that is S2, and then you have an S3. So that is sigma of similarly UX3, right? So UX3 plus W is 2, that's S3, right? So once you have computed S3, that's the last word in your input sentence. So it's now time to make a decision. How do you make a decision? You once again you do a linear combination. You do V S3 plus some bias, but we are ignoring bias. So this will give you a vector of length 3. Okay. And what you now need to do is you need to do a softmax on top of this. And that will be your y hat. Okay. So this is for a fixed sentence, right? Three words. But in general, if the input,
So,
yeah,
so, sir, in lectures, I have seen that the arrows, upward arrows, are on every
correct,
sigmoid.
yeah. So we'll come to that. So for sentiment analysis, you kind of can get away with just one arrow at the end. It depends on the problem, right? So I'll discuss another kind of problem where arrows will be everywhere. Even in this problem, you can have arrows everywhere. Okay. So, but this is one kind of RNN. Okay. So you must, this is like the simplest of the lot. So in general, if the input is,
Sir, I have a basic question. One question, sir. You say that x1, x2, x3 are word embedded, matlab W word, and it is coming from the SIBO. Then, if it is coming from the SIBO, it know the W context. Now, then why we are doing again?
no. So so those contexts are very narrow, right? So from SIBO, if your context window was what, maybe 5 left, on the left and on the right, it was 5 words,
Okay.
right? So that is one thing. The next is usually what ends up happening is, so that scenario is called pre-trained, using pre-trained embeddings, right? So using SIBO is that would be a scenario where you use pre-trained embeddings. In reality, you might learn the embeddings also from scratch. Okay, so that's an end-to-end learning setup where the embedding itself is learned. Okay, so we can also discuss that, but yeah, so using SIBO or what some other word embedding is a pre-trained setup. Okay, so if in general if the input is x1 to xt, then what you do is you can specify the state equations as at some time step t or time step I, st is sigmoid of uxi plus w s t minus 1. Okay, with s naught equal to, let's say, 0. This is one, let's say, one possible initialization, right? All zeros. Then you can define, then for some t in, say, 1 to capital T, this is how it look like, right? S1, S2 till ST. And finally, at the last time step, if you want to make a prediction using the last state vector, what you can do is you will do softmax of V S capital T. That will be y hat, and the loss will therefore be, if you are using, what are you using? What is the spelling? Okay. So negative log the base E of y hat true label, right? So let's say L is the true label. It could be positive, negative, neutral. That will be loss of y comma y hat. And then what you can do is you can back propagate. So the back propagation part we'll kind of, I don't want to skip, but let's put it off for a while. I'll first discuss few more problems and get back. But is this general idea clear? So the equations in general should be xt. Okay, can we move on?
Sir, this cross entropy loss is that of that feed forward network. That's same.
Same cross entropy, yeah. Yes.
And in this case, there will be 3 that neutral or something, whatever it is. So whichever is the positive one, true one, that we will take here. Others will be 0. That is.
Others will not be 0, but you will only use the predicted probability corresponding to the true label. So,
Okay,
for
okay. There will here it will be sometimes the prediction may not be true, isn't it?
that is immaterial, but yeah, you will use, like, for example, if the true label is positive, you'll use minus log 0.7. That will be your loss.
Sir,
Okay, sir. Fine.
Okay.
sir,
Yeah.
will there be any criteria like above 0.5 we will be considering as a positive and below that negative like that?
So you, yeah, you could do that, but what might be better if you have many classes is max of this vector, right? So it could be like 0.4, 0.3, 0.3, right? So in that
Okay.
case, I might want to consider whichever is the maximum as the predicted.
Sir, then one doubt is that so excellent is speaking out here, okay, for example, and we are adding one but statement and mentioning it's too lengthy, for example.
Sorry, we are
Like movie was excellent, but it was too lengthy. We are adding one statement.
right.
Then sentiment analysis will be going till that last statement, right?
It will.
Go to the last statement. For example, it will go to movie was excellent but was lengthy, right? So till lengthy it will be going and then only it will be predicting like.
Yeah, yeah, yeah.
But actually this should be a neutral review, right? Because it was lengthy, right? Then max of something will make a sense or something. But just asking.
Yeah, yeah. So there are different approaches, right? So one approach is to have the instead of taking only the hidden vector at time step 3, what you could do is you could so alternatives to taking the last hidden state alone prediction, what they have in the literature is, to have an average of, say, s1 plus dot 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 plus s10 less st, right? So
Yeah.
you could divide this by t, and you could call this the average state vector and use this for prediction, or you could use max of this across the t time steps. You could do all these variations, but this is one standard way of predicting uh, the final label, especially if you want to convert a sequence to a single label. Okay,
Okay.
so you could, yeah, there are variations where you don't use just the final hidden vector, final state vector, but you use a combination of all the state vectors across the t time steps. That can also be done.
Okay. Sir, could you write the parameters calculation also, if possible?
Yeah, so the parameters are going to be, so if you copy this again, yeah, so typically, let me call this, I use a dot 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 to mean that there are many time steps here. This will be V capital T. Okay, right? So there are some errors in lectures. If you notice errors in lecture slides, which we have to make a note of. So xi is in Rn. Okay, so xi is in Rn. So it could be 300, depending on the word embedding. Could be 300 or 200, whatever. Each state vector has the same dimension. Okay, so I'm just doing it for one set of values here. Let's call this D. Okay, so the hidden state dimension is D. So the state vector is size D. Therefore, this matrix U is converting from N to D. So it will be N cross D or D cross N.
D cross N.
Yeah, it will be D cross N. Okay.
Professor write it wrongly. N cross
Yeah.
D.
Yeah. So this is D cross N. Now, what will be W? What will it be?
D cross D.
It will be D cross D, right? So the hidden weight matrix is always going to be square. Okay, it is going to take one state vector and convert it into something of the same shape, right? So it is going to be square always. Finally, you have V. So what is V? Assume that you have
Number.
K classes.
So K into D.
Yeah, so it's K cross D, right? So that's going to convert your hidden state vector into K classes, right? Probability distribution over K classes. I mean, before that, right? So softmax, then we'll make it a probability distribution. Okay, so those are the three parameters. So this is a simple RNN for sentiment classification. Yeah.
So, U is D cross N, that one I understood. But W cross S naught would be D cross D, right?
Yeah,
And
S
how
naught is
will
D, so W is D cross D.
so S naught is D, W is D cross D, that will be D cross 1, right?
What will be D cross 1?
No, no, W only S naught. What will be that dimension?
That will be D.
D, right? That okay, technically D. So D cross N will become, and this will become D cross D or D cross N minus K. This S1. This one dimension I did not get it.
S1 will still be D, right? You have this is this whole thing is D. This is also D.
Oh, okay. U, okay. D cross N cross N. Okay. Then it will become D cross. Okay, got it. Yes.
Okay, so that is the equation of equations and okay, bias. You don't. So bias is boring. Okay, I didn't never consider the bias, even though it is very important, right? Your bias should always be there for a neuron, but then this plus B makes things boring. So you have to keep on adding this plus B everywhere. So we generally ignore the bias, but not that bias is there. You can, in fact, include the bias as a part of the weight matrix itself, right? By adding one more a neuron with value 1, right, which is always 1. Things like that you could do, right? So I hope you can manage what will happen. If you have a bias, you will have one bias for every neuron, right? So here you will have one bias, here you will have another bias. Okay, I hope you can figure that out. So the same bias, right, by the way. Since the weights are shared, the bias will also be shared. You won't have a bias for every time step. You will just have a plus B, plus B, plus B everywhere. Okay. So that completes RNN for a very simple case of sentiment classification, right? So what we'll do is we'll consider RNN architectures for other problems, right? Other NLP problems where things are not so straightforward. So we'll take this itself. Okay, now consider this problem of what is called part of speech tagging, right? So this is an interesting problem in NLP where let's say you have a word, you have a sentence. What is the sentence? The so that okay. Okay. So okay, a beautiful flower. Okay, this is a sentence. Now there is this concept called part of speech in English, right? So you have what is it? It's called a determiner, I think, right? I'm not a article, right? So A is what an article. What is beautiful in the context, in this context?
Adjective, sir.
It's an adjective, right? So, and what about flower?
Noun.
It's a noun. Okay, so you have a finite set of tags. So these are called tags. So this could be article, whatever you have seen, right? Adjective, noun, adverb, pronoun. Okay, and what else, right? So assume that these are all the parts of speech that you have. So one problem in NLP, right from classical NLP times, is given a sentence, you have to determine the part of speech of every single word. Okay, so notice that this is different from the previous problem. In the previous problem, you had a sequence, and the sequence had only one label, positive, negative, or neutral. But now the sequence, every word of that sequence has a separate label. Okay, so this is called sequence labeling problem. So just some terminology where every term or every part of the sequence has to be labeled. Okay, so this is where what happens is it's not enough to produce an output at the end. You need an output at every stage. Okay, so this is a y1 hat. Okay, so this is now going to be a y1 hat and a y2 hat and a y3 hat. Okay, so y2 hat and y3 hat. So now how will the equations change? So where did we write this down? We wrote this down here, right? So remember, the state equations will not undergo any modification, but then you are going to have three separate equations, right? So one for each time step. So you have a yt hat. So you'll have y1 hat is equal to softmax of s1. You'll also have y2 hat, which is softmax of at that time step, right? So whatever information you have at time step 2. Likewise, you'll have a y3 hat equal to. Okay, so what will your loss look like now?
I believe it will be summation of all three.
Yeah, it will be summation of three loss function, three cross entropy losses, but at different time steps, right? So there's a log to the base c of y1 hat at the true label, right? At let's say L1.
Base 3 or base C?
Sorry, base c. Okay, so this is minus log to the base c of y2 hat taken at the true label L2, right? So remember, y2 hat L2 is a single value, it's a scalar. And finally, log to the base c of y3 hat taken at true label L3. Okay, this will be the loss, and then you have to back propagate the whole thing if you are learning the weights. Okay, so that is for sequence labeling tasks, wherein every term of the sequence has to be labeled. So one more very popular framework, one more popular problem is the one we have been seeing so far. So language modeling, right? So where you want to predict the next word of a sentence given the current set of words. So this is also a sequence labeling task. Okay, but here, how will it look like? So if you have a sentence like a beautiful flower, what you should do is you will pass a as input. Okay, so beautiful flower. So this will, well, it will produce a y1 hat, a y2 hat, and a y3 hat. Okay, but important thing is during training, what you will do is, what is the true label corresponding to this position? Y1 hat is the predicted label vector. What will be the true label?
You mean this beautiful?
Yeah, so you want to predict the next word given the current word, right? So this will be beautiful. This will be, you want to predict flower here. And usually what you want to do when your sentence comes to an end is you want to predict what is called an end of sentence marker, right? Something like this. So this also will be a part of your vocabulary. Okay. So typically what happens is when you are trying to learn a language model, you don't just go with pre-trained embeddings. Your whole goal is, to learn embeddings using that corpus itself. So how these equations will get modified is, let me take the, where is that time step t fellow? So this one was there, right? So this is your ST, right? Now you will have something before ST. So this is not really from the exam point of view, but I'm just giving you this idea. So you will have your one hot vector. So assume that xt is your one hot vector. So what you will learn is, you will first extract the embedding corresponding to xt, okay, using what is called an embedding matrix, and this will be something called et. Okay, this is your embedding vector, and then the rest of the equation remains the same, but then instead of xt you will use et plus w st minus 1, okay, and your yt at time step t, this will be v st, okay. Usually what they do is, this v is going to be, so e is called the embedding matrix. Can someone tell me what the dimension of e will be if your vocabulary is of size v and your embedding dimension is d? What will be the dimension of this matrix e?
Excuse me, sir. I didn't get to what you are telling. This this A is the word, isn't it? So there should be some more words corresponding to that. Is it what you are telling? This embedding by embedding?
No. So I need an embedding for a, right? I need to learn a word embedding for a.
I mean choices for the next word.
No, word embedding, right? So like a vector for a. See, so
Vector.
far we have assumed that xt is that vector, but now what I'm telling you is I can actually learn that xt itself,
Okay.
or an embedding for that word. So
it's v times some k, because SVD will reduce the d to k. So
no, we are not using svd, right? So we are actually just
So it will be V cross V, right? Sir? Because
it will be d cross v, right? I need to convert. See, xt is one hot encoded.
technically D cross V cross D cross V. Both will be D cross V, I guess. X and E will be same.
No, xt is one hot, right? So it is just going to be one. It's a vector of zeros with one somewhere.
So then how will it be cancelling, sir, in multiplies?
We don't need it to cancel, right? This is d cross v. I need my embedding vector to be of size d. See, earlier I said embedding vector xt is of size d. Now what I'm saying is xt is some one hot encoded vector, and I need a d-dimensional vector here.
So still we will get B, right? That's what.
D, right? D
B,
cross
B,
v
B.
and v.
No. So one hot encoding will be V cross 1, you are telling?
Yeah, v.
That's what I am asking. 1 cross, okay, V cross 1.
Yeah, it's always v, right?
You understand. One hot.
Okay, so this is what happens. So typically v, right? V is called the unembedding matrix sometimes because it takes you from your embedding space of size d back to your vocabulary, right? So, and this will be, if you think about it, it will be v cross d, right? So u in this case will be what? I will retain it as d. In fact, in this case, both u and d will be, w will be d cross d. Okay. So this is a common practice that you will see in RNN based language models. So since this is v cross d and this is d cross v, it is actually a common practice to do what is called weight tying. Okay, we discussed this weight tying also. And instead of having a separate matrix called v, they will use what is called an unembedding matrix, which is just the transpose of v. Okay, this is a common practice. So this is just
So shared number of it would be one time train, right?
you will only have to store E because V is just E transpose.
So D cross V would be only be trained. V for V we need not train separately, right?
Yeah, you will just need to store E.
Okay. And one more doubt I have. So in S naught comma A is denoting x of 0, right?
So yeah, what is the initial state vector? I am also not exactly sure. So I need to look up few
Because
resources.
I my doubt is that initial state vector is -1 or 0 because we are considering x of t, right? So it is x of 0, right?
Which is 0.
No, x of t we are considering, right? E of x of t or small e t we are considering e of xt, right?
Yeah,
So if t is we are considering t as 1 means s of 0 is the initial state.
0 is the what?
Like for example, we are considering t small t as 0,
No, E0. There is nothing called E0, right? It starts from 1.
but it's the initial weight, right?
It is not a weight, right? E0 is not the weight. E0 is there's nothing called E0. E1, E2, E3. They're all embeddings for X1, X2, X3. There is only S0. The 0 is only for the state, not for the
Okay.
embeddings.
Okay.
Sir, E is a learnable parameter, right, sir?
Not E. Sorry, yeah, E, yeah. Well, E is what? Capital E, you mean, right?
Capital E.
Yeah. Capital E is a learnable parameter. Right. So earlier, what we did was we kind of subsumed this E, fixed the E, and said that it has already been learnt using CBOW. But what we are now doing is we are learning that representation itself through the RNN with the help of the RNN. Okay. So these are RNN. So there are many ways to now learn word representations, right? So word representations can be learned via SVD. They can be learned via CBOW and uh, skipgram. They can also be learned via RNNs. That's the lesson. And we'll see in the future that it can not just RNNs, you can learn them using what are called transformers. Okay, so that will be the last week. Okay, so any questions so far in what we have discussed?
Sir, this embedding matrix you told, no, that is will be different for these different inputs, isn't it?
No, that will also be fixed.
Mean for x1, x2, etc. Everything, all for all these words, it will be same.
The embedding will be different, but the embedding matrix will be fixed.
Sure. Could you tell me an example that I am not clear about that? If this is A, what will be this embedding? It is ones and zeros only will be there, isn't it? Because
No. Only in XT you will have ones and zeros. EXT will be some column of the matrix E. So each column of E corresponds to some embedding. There are as many embedding columns, as many columns as there are words in the vocabulary. So XT will be some one hot vector. So if you multiply E and XT, you will extract some column corresponding to that word.
so that it will represent this word A or
Yeah.
word beautiful.
Yeah.
Okay.
So sir, xt can be told as a context.
No, XT is not a context, right? XT is the word at time step T.
So ext is the
EXT is the embedding corresponding to the word at time step T. It's not the context.
okay. So embedding means we are storing some percentage of a value of an xt, right?
It is some representation of a word, right? That is what an embedding is.
That is that this E matrix, that capital E matrix is some which represent the whole vocabulary, isn't it?
It represents the embeddings for every word in the vocabulary.
That means only for this particular input which we give. That like a beautiful flower or any other sentence which
No,
we
if there are
give.
100 words in your vocabulary, there will be 100 columns in your matrix
Matrix.
E.
One column for each word. Okay.
Yeah, yeah. You have seen word embeddings, right? So we
Uh,
learned word embeddings using CBOW, right? Same thing here. That also had one column for every word. SVD also had one row for every word. Likewise, E will also have one entry for every word.
Okay. Sir,
Okay.
then can I ask a question that to this week's, that is 10th week graded assignment is there? No, that we have to do with some Python programming, isn't it?
I have not yet looked at it.
Because it is this RNN network, we have to create an RNN network and do those calculation, etc.
Okay.
But the details, that means this initial weights, etc., has been given as an NPZ file.
Okay.
So that means we have to do this coding. Then only I will be able to calculate this. There are so many.
I think so. Yeah. Yeah.
So, but such a thing has not been in any lectures. Could you suggest some source where we can have some reference
For what?
for this type of coding?
NumPy, you know, right?
Yes.
That is all, right? That's just NumPy. So it's, if you know how to use NumPy, multiply matrices, that is all there is to it, right?
Matrix multiplication we can do. I can do. Okay.
That is all there is, I think. So it's just matrix multiplication and some functions. Okay. So yeah, that is RNNs. Now, any questions regarding RNNs from anyone else?
So can we solve some problem on
Problems.
Back propagation of coordinate.
Yeah. So maybe I'll do more of the theory today. Problems. I think there'll be separate PYQs that you guys will be doing, right? PYQ sessions. I actually haven't come prepared with any problems per se.
not today, sir. Any day on Friday or something.
Friday, yeah, Friday. Maybe we'll move on to week 11. So yeah, maybe back prop and LSTM, right? So I'll quickly do both. I won't do the full back propagation because it's hard. So what I'll do is I'll just take up simple values. So this will be I'll just take up scalars. Okay. And for 2 time steps and show you
Sir,
what.
for simplicity, can you mention it as U1, U2, and all? It's confusing for me, actually.
No, right? It is not U and U hat. It is U only everywhere.
It's not. It's different, right, for every state.
No. It is same parameter sharing. You are using the same U and same W. That's the whole point, right? Otherwise, it won't work, right? So the
But
whole
it's
idea is,
weighted average, right?
what is weighted?
No. For X, based on X1 only, W will be changing, right?
For what W will change?
No. Based on X1 only, and W will be determined by X1, right?
No. W is independent of X1, right? W will be learned from. You can learn W from different X1, X2 pairs, X1, X2, Y hat, Y pairs. But then W is not going to change depending on X1, X2, and X3. It will change after every iteration. It learns from X1, X2, and Y. That is true. But then it won't change because there is X1 here and there is X2 here, right? So it's the same W.
So I did not get the point. So learning and changing, what is it?
No, I also didn't get what is your question actually.
No. You mentioned like every iteration it would be learning out. So I thought it would be changing every iteration.
Correct, it will change every iteration, but then you are in one iteration, right? You are like in the middle of an iteration. So how will this W be different from this W? Iteration is not xt, right? X1, X2, that is not what we mean by iteration here.
Okay.
So this entire thing is one time step. So, or so there are two times here. One is for processing the sequence, and there is another larger different time step, entirely different, where you are updating the weight vectors. So if you add if you want to add time step here, it will be some other time step. So it should be some wi ith iteration, but this will also be wi. This won't be I plus 1.
Okay. Okay. Yeah, fine, fine. Now I understand. Now I understand. Same thing will be for you also.
Yeah, so you vw get carried over. So what you are doing is this process is called unrolling an RNN in time. So the RNN is actually one single object. So it is I have unrolled it. So if I give an input, if the input is x1 x2 comma y, then how will the RNN work? You will pass pass x1, then you will pass x2, then you will get some y hat. So that I have expressed in this form. Okay, actual RNN is all three things put together rolled up into one. Okay, so let's look at forward, only then we'll understand the backward. So what is forward going to look like? S1 is sigma of ws naught plus ux1, right? And S2 is sigma of ws1 plus ux2, and then y hat is S2 of vs2 softmax of this, right? So that's your forward pass. Now let's try to compute. So all of these things are scalars, right? To keep things simple. Now I want you to find out the partial derivative of the loss with respect to, say, u. I want to find dou L by dou u. Okay. So what is happening here? Now, if I want to find dou L by dou u, typically how will you go about it? You will first find what? Dou L by?
Dou V.
You will find dou L by not dou V.
Y
See,
hat, Y hat.
dou V is once again a parameter, right? So we'll find with respect to y hat, right? As
Y
we have.
hat. Yeah.
Okay. So first y hat, and then y hat with respect to what?
S1.
S1 is still out there. You are still here. So I'll
S2,
find,
S2, S2.
right? So into
Sorry. S2.
dou y hat with respect to S2, right? So far it's easy. L by y hat you can find out. It's not new. Y hat with respect to S2 also is simple. It's just V. Okay. And not V. What will it be? It will be something else, right? Because the softmax intervenes. So you'll have to be careful. But as I'm assuming that that's not too hard, because this is just the feed forward part of the RNN. So till this I'm not computing. Okay.
Sir, will this be the error itself? YL, dou L by dou S2.
Yeah. So you can treat it that way, because will it be error? No, not S2.
Weight of error, right? V
Yeah,
into
yeah,
error,
V
right?
into the error you can, yeah, there will be V into the error, but you can, that part I'm assuming you know, right? So what we are interested in, what's tricky is dou S2 by dou U. Okay, it's this part which is hard, and that's what we'll look at now, dou S2 by dou U. So and we'll concentrate on this. So what is S2? How does S2 depend on U? Okay, so that's what we are going to look at. First, notice that I'll rewrite S2. Okay, so S2, if I want to treat it as a function of different quantities, is actually a function. It's a function of W, but then remember that we are computing partial derivatives, and W is kind of it's a constant, right? It's not constant, it's fixed. So when you're taking partial derivatives with respect to the parameters, what do? You fix one parameter, sorry, you fix all other parameters and allow only one to vary, right? So that's the idea. So what is varying here? U, right? So this is a function of U for sure. W, you don't need to worry. X2 is anyway an input, right? It's an activation, input activation. So X2 is also fixed. Remember that your loss is only a function of the parameters and indirectly the function of the activations, right? So X2 is not an activation. It's only an input activation and it's fixed. W is another parameter, so you don't need to worry. But S1 is kind of going to vary, right? So why is S1 going to vary? Because S1 itself is a function of U. Okay, so you have to be careful. So S2 now is a function of U and S1. So remember, we want to find dou S2 by dou U. So there are two ways to solve this. One is using the chain rule. What will happen is, this is nothing but, so dou S2 by dou U, right? So it's dou S2 by dou. So there are two values it's dependent on, right? Dou S1 into dou S1 by dou U plus dou S2 by dou U, where if you look at the lectures, Prof would have used a plus sign here, where you kind of treat S2 as a function of U alone, right? Okay, so what does this mean? It means that you treat S1.
Sir, one question, sir. Is it a S2 by del U, or it is del S2 by del W? For that you would do this.
For U.
Okay.
See, W, when you are doing it for U, W is kind of fixed, right? So it's like a constant. So that doesn't feature, so it is not a function of W. So you won't treat it as a function of W.
Okay, but W is also have a same problem. No? W is dependent on the previous W.
But it's a constant, right? As far as you are concerned, as far as the partial derivative with respect to U is concerned, it's a constant.
No. So I am saying that is it this rule is for del S2 by del U or del S2 by del W? That is I am a question.
So we are doing this for del S2 by del U.
Okay.
Similar exercise you'll have to do for W.
Okay.
Okay. So what will this be? Del S2 by del S1. So you are treating S2 as a function of S1 now. Okay, partial. You are taking the partial derivative with respect to S1. So what will you get? So it's
It
a
is sigmoid, yeah.
Yeah, so it's a sigmoid with respect to its, so first sigma prime. So that's just S2 into 1 minus S2. Remember that you have a sigmoid, so that will be in F sigma prime is sigma into 1 minus sigma. So you will first get S2 into 1 minus S2.
Then
and
W1.
Then W1, right? You have to differentiate with respect to S1. So that's W1. That's this term. Okay. Now what is this treated as a function of U alone? Same. So this is common. If you're treating this as a function of U alone, I mean U in the sense where S1 is different from U, right? Independent of U. Then if you differentiate, what will you get?
0. It's constant.
So why it is W1? W was fixed.
Yeah, but you're differentiating this with respect to S1, right?
This one?
Oh,
then
sorry.
It,
Oh, okay. This, sorry, yeah. This is just W.
W into plus so it will be X2.
X2, right? So this will be the value of, this is what it will be, right? Where is this? Yeah, this will be.
Sorry, how X2, sir?
Yeah, because there is an X2 here, right? So if you differentiate
No.
X2 with respect to
Sir,
U.
we are differentiation it as separately, right? So it will be constant for the first iteration, right? When we are considering S1, then second part will be constant. Like that only chain rule applies, right?
No, so this you understood, right? You are treating S2 as a function of so S2 is now treated as a function of two independent variables, U and S1.
Yeah, that I understood. And we want to actually calculate based on U, but S1 is interfering in this case. So we have to differentiate in both the ways. So we are first differentiating for the whole term sigma first. Then we are getting S2 in the 1 minus S2. That one I understood. And within the bracket, how did W plus X2 go? X2 go? That one only
X2 because you are treating it as a function of U also, right? It's a function of both U and S1. So you have to differentiate with respect to U alone, assuming S1 is a constant or independent of U. So that will give you U X2, U will disappear, you will get X2.
Okay, so okay, fine, fine. So dou plus S2 by U is nothing but dou S2 by U into S1 by something. Right.
No, S2, this is just differentiating the function f of u comma S1 with respect to U, treating S1 as an independent variable. S1 and U are independent variables now.
I have some. Yeah, fine. I
Okay, so this is one way of understanding it. The alternative is, if this is all confusing, this dou plus notation is confusing, what you can do is, here you can do it, but in general you can't. So this is ux2, right? This is S2. This is what you have. So you have to find out dou S2 by dou U, correct? That's what you want to do. So this is approach one. This is approach one, where, so what is approach one? You apply the chain rule for partial derivatives in a specific way. Approach two, what you do is, get rid of all recurrences, meaning this is S2. Okay, so let me write it again. So S2 is sigma of ux2 plus wx1, right? Sorry, ws1, correct? What is this in turn? What is S1?
UX1,
Sigma of ux1 plus
WS0.
ws0, right? So now this is kind of easier to work with because this you can understand, right? So S2, remember, now you can treat it as just a function of u. Okay, so of course it's a function of u and w, but you can clearly see that u and w are independent. Here it is quite clear that u and w are independent, and you can go ahead treat w as also a constant. So now what will you get? So it's like dou S2 by dou u is once again this S2 into 1 minus S2. Okay, and then you have to differentiate this. So here if you differentiate, what will you get? You will get X2. And then you'll have this here you'll have to apply this W will be there, but then this once again another sigmoid. So this will be S1 into 1 minus S1. And then what will you multiply this with?
X1.
X1. Okay, so if you go back, we should get the same thing. We didn't get, so which means we have made a mistake here. So where is the mistake? So let's see. So okay, this is the correct one because this is unambiguous. This has to be correct. So X2 is correct. This W into S1. So that one we missed. Let's go back. So what did we do here? We are trying to find dou S2 by dou U. So we said that this is a function of U and S1. Dou S2 by dou S1. Let me write this again. So dou S2 by dou S1 is S2 into 1 minus S1. Okay, that's the dou U part is where we missed. So that is S2 into 1 minus S1. Dou S1 by dou U is that is where we missed. So
We have to split it again, I guess.
So this one, let's add it here. So it should have been. So okay, so this is dou S1 by dou U. So that is once again S1 into 1 minus S1 into X1. Okay, that's where we messed up. And now this is dou S2 plus S2 by dou U. That's just the same thing. So you treat this whole thing as a function of independent variables U and S1. So this will be sigma S2 into 1 minus S2 into the derivative of this internal quantity with respect to U. So that will be X2. Okay, so that is what we should have. S2 into 1 minus S2 into S1 into 1 minus S1. Did we miss something? Where is the W? There is
It's
a
10 o'clock.
There's a W also over here, right? S2 into 1 minus S2. S1 with respect to W. Okay, yeah, there will be a W. This W, right? So what is this W? You get it right? I made some mistakes here. So this W is this W. And then there's a dou S1 by dou U. So there is a WS1 into 1 minus S1 to X1 plus X2. So did everyone get this part? There were a few back and forths.
So second approach can you show? I think that's it.
Sorry?
Second approach can you show? I understood that better.
Yeah, so second approach is anyway, you just replace the whole thing. But yeah, is this clear to all of you, the two ways of doing it? Any doubts? Okay. Yeah, so that is that.
So, sir, I have one very basic question. Can you go to the start of the derivative? Full start, when you start the, yeah. So, just a minute, sir. Maybe just a very basic question I am asking. Del L by del S2, it should be y hat minus y, na?
Del L by which
It
one?
is,
Del L by?
it is full term. Del L by, this total term will be y hat minus y, correct?
Not S2, but the pre-activation here, right? So just before the softmax, that will be y hat minus y. So del L by del 8, so you can call it maybe A here, whatever you come. So see, S2 into V is some A, right? So the dou L by dou A is y hat minus y. And then dou A by dou S2 is some V.
So means S2 into V. Okay. There is a pre-activation is happening. Okay, I missed
Yeah.
that one. So there is another neuron is there actually. Softmax neuron is there.
Yeah, that's a softmax sitting here.
Yeah. Sorry, sir. Very basic question.
Okay, right. So dou L by, yeah. So this thing alone, I'll maybe do it again. You see, what is happening is dou S2 by dou S1, right? So S2 with respect to S1, you have to first calculate the sigma prime. So that is S2 into 1 minus S2. Okay. And then with respect to
S1.
with respect to S1, so that is W. Okay. So that so far I have just computed dou S2 by dou S1. Okay. And now there is a dou S1 by dou U. So what is that? S1 with respect to U. Once again, I have to do an S1 into 1 minus S1. That will take me inside. And then with respect to dou U, so that will give me an X1. Okay, this is the first step. So now we come to this part where you treat it as independent functions of U and S1. So there, this S2 into 1 minus S2 will be there again. That's why I've taken it out. And then you differentiate this with respect to U. You end up getting an X2. Okay, this thing is simpler, the second approach. So you express the whole thing just as a function of u, and then you are done. So okay, so LSTM, do you want me to discuss or shall we close here?
So close here tomorrow. Can we connect LSTM with the phrase mode?
So
Tomorrow,
Friday would be better. So tomorrow I
Okay.
have class ST, software testing.
tomorrow also is tough for me. LSTM, I'll tell you where to look at. So I'll just repeat whatever is done there. So one is that Juravsky and Martin, you can look that up. So the other is a very good article which I will share. So this is these
So
two
do,
resources more than enough.
so do I want to remember the equation of the LSTM like that read, write, and these equations?
Yeah, you have to remember, but it's very easy to remember, which is what I'm trying to say. So it's just that uh, if you read the right resources, you will understand it very well. So this will give you a step-by-step introduction to understanding LSTM. So this was a great resource when it came out first time. So see, I'll just basically tell you what is there, and then you can read it tomorrow. You will get it. So what is happening is there are four operations that are happening. One is an LSTM knows how to forget, it knows how to write, it knows how to modify the input. Okay, roughly three. Okay, so there is so whatever the prof calls as ST is what is CT here. Okay, so original paper it was actually CT. So you have one vector running through which is called the context vector. Okay, they call it the cell state, but you can actually think of this as the context. So remember I told you that your hidden state is performing two functions. It is storing the context, that is one function. It is also making a decision at every time step. Okay, so what LSTM authors have done nicely is to separate these two functions. So there is one vector called CT which will only keep track of the context. So remember that it's just going from left to right. And then there is another vector that is pushing out the information at every time step. That is called HT. Okay, how do you, so the whole idea of LSTM, the equations is how do you convert the previous context to the current context? Number one. And how do you convert the previous output HT minus 1 to the current output HT? Okay, so you do it using what are called gates. Some gating mechanism is there. So they teach you how, what are these gates. So there is something called a forget gate that tells you how to forget, what to forget. There is something called input gate that tells you what to write, what to remember, sorry, what to write, what new information to write. And then what you do is you combine the two pieces of information to produce the new cell state or the new context. Okay, so rest of it is the final part is how to write. So what should you output as HT? Finally they put all of this together. So this is like one big equation. So these are all variants, but yeah, this is one big equation. You will see some for the states, some for the context.
So basically, I need to remember these equations because
Yeah,
I.
so the three gates, input, output for gate, and then the two states. So the context state and then the output state. So whatever the prof calls as ST tilde and ST, you have to remember.
So is it not possible, sir, one session on this?
Not right, not tomorrow, not this week, but we can do it maybe next week. I don't mind doing one. So eventually we can do before the exam one on LSTM.
One on LSTM, another on transformer, I believe. Attention or transformer.
Yeah, so yeah, two more we can do. Yeah.
Yeah, yeah.
Okay, so that's all I had. I'll share these notes after cleaning them up.
Hmm.
Okay, so we'll
Thank
meet
you.
again next week.
So
Yeah.
previous notes are shared or I did not.
Which ones?
Day 4 yesterday when those sessions were there, right?
Yeah,
Those slides, do we have it?
not yet, not yet. I have to. So though that's the one I have to clean up. So they're all there, but they are kind of very patchy. Here and there, I have written things. Uh, I'll try to do some basic cleanup and share it.
Okay, sir. Sir,
So
one
this
more thing.
LSTM
LSTM.
resource link which you shared in the screen.
Ah,
Where is that, sir?
yeah. So I'll share it. I'll share it on the group.
Okay, sir.
Sir, in last 4 weeks, do we have like numerical intensive questions or theoretical, sir? What
Both will be there.
okay. The equal distribution would be there.
Yeah, we'll have both.
Okay, sir. For syllabus of NTEM would be more concentrated on last 4 or it would be equally distributed?
That we will tell you. So it will be at least 50% from last 4.
Okay. And 12, week 12 also will be there, right? For sure.
Yeah, all 12 weeks will be there.
The problem is that in the last 4 weeks, they are not given any problem to solve. So numerical problems are not there.
Yeah, so the PYQs are the only
Mhm.
thing you
Yeah,
can
yeah.
rely on there. Yeah. Okay. So we'll
Okay,
meet
sir.